Yeah, g'day, Stephen Barter here. How are you doing on this yet another great day? Me, well, I'm still excited, still looking forward to bringing you more information and more valuable lessons. And today is no exception. Today I've got a really important lesson, and it's tacking on to the first two lessons that you guys have already been through. Really important information. Again, something that has escaped lots and lots of moulding shops until today. So I'm no longer confused, but I'm damn excited, and I can't wait to bring you this next lesson. Okay, here we go, Module 3 of ProMold Professional. So today we're going to talk about the final chapter in our heat exchanging process, and that is the blow air pressure. And there's a lot to blow air pressure. It's not just about the final pressure, so we're going to cover off a number of components there. But before we start, all I want to do is just again remind you guys what's going on here. Every machine and every situation is different. This information is recommended based on real experience and best practices. All responsibility is with the operator conducting business. So guys, just be very aware of what you're doing as you're taking the learnings. They're all good. They're all based on real life results, and they've worked for me every time. So let's jump right into it. So as we touched on, we're going to be talking about the air pressure today of our heat exchanging process. So as you can see there, the air pressure we've got is going to be pushing the plastic parison against the mould wall. Now we need a certain amount of pressure to be able to do that. Now if we don't have enough pressure, then the heat exchanging process can't actually take place. The air will not force the plastic parison to the steel, and then therefore the steel can't draw the heat out of the plastic parison efficiently. So it's really important we get that air pressure right. But it's not just about the air pressure. It's also about inflation rates, exhaust, and a number of other components like that. So what we're going to do is just, as a bit of a guide, we're going to start using our air pressure of around 100 psi. Now that's a general purpose pressure, and I'll cover off a little bit more things in front of you right now. So let's talk about pressure needs. So if I'm inflating a 2 litre milk bottle, I have a very thin wall thickness. So it's really easy to get that diaphragm effect of pushing the plastic against the side wall of the mould and enabling that heat exchanging process. But on the other hand, if I have a 20 litre container, in this example that you can see on the screen, it has a very thick wall thickness. So this particular container might be just over 1 kilo in thickness, in weight, sorry. Therefore, the plastic thickness is much greater. Now, the plastic temperatures are roughly the same, but we've got to force the plastic into every nook and cranny into that mould cavity. Now, to be able to do that, we need adequate air pressure. Now, if we don't have adequate air pressure, then we're not going to get that heat exchanging process. So as I've mentioned down the bottom here, the thicker wall thickness requires more pressure. Now typically I would run a 20 litre industrial bottle at around 120 psi. That's a nice figure. But you know, a 2 litre milk bottle can quite easily work on 100 psi, whereas a 20 litre heavy wall industrial bottle does need that more pressure to make sure that we can force that plastic out to the side wall of the container. So there you have it. Thicker wall sections require more pressure. So let's talk about the inflation rates. Now this is really important. Now why is an inflation rate so important? Well, what I've got here is a picture of a blow-pin tip. So you can see the blow air tube here. Now the diameter of that blow air tube is critical to the air pressure and how quickly it builds up inside a cavity or inside a bottle. So when we get to the final pressure, and we'll use the number 100 psi, well, that's really important to holding the plastic against the sidewall, but how we get there is equally important. So we want to get there as fast as possible. So the way to do that is to have a diameter of our blow-pin tube, a minimum of around, I like to use it a minimum of around 8mm diameter. Now we don't want to go too big, because as we're inflating the opening of the bottle, when we're bringing the blow-pin into the neck, we don't want air going everywhere, and that may cause us other problems around parison entry into the neck. So an 8mm tube is typically a good number. So what we want to do is we want to increase the air pressure at a fairly fast, steady rate, and then of course it'll taper off at the end. Now, I've seen many examples of situations where the blowpin tube has been, say, 5 millimeters or less. Now, what that means is the inflation rate is slowed right down. Therefore, it takes a lot longer to get up to the 100 psi pressure. So, the way I look at this is a very simple test. Is if I can't blow through a blowpin tube really easy by putting it in my mouth and blowing as hard as I can, how is the machine going to do it? So we've got to make sure that we've got a good size, or the best size blowpin tube that we can for that particular product. Sure, if you've got a small neck, you're going to have a small blow tube. But if you've got a big neck with a small blow tube, then you're just going to create other issues. So what are some of those issues? Well, first of all, if you're inflating a bottle into the shape of a cavity and you've got a corner just like this one, what we're going to do there is having trouble inflating the air at a reasonable rate. So as the air pressure inside the parison, inside the mold, increases slowly, there is a trapped air component just inside here. Now that trapped air component will struggle to get out at a great speed. And what that means is the plastic will actually mold around that air pocket. It will also start to cool down, so you'll end up with a orange peel effect and some uneven finishes on the surface of the bottle. But the big problem is that molding around that air pocket. If you don't get the air out quicker by pushing the parison from the inside out to the mold wall, you're going to get thin spots in your panels, your corners, and around your shoulders. And what that means is a reduced top load. It may even mean failing drop tests and other components like that. So what we've got to do is we've got to increase the air pressure as quickly as we can. Now on the flip side, let's talk about the exhaust pressure. So with the exhaust pressure, if you have a gauge on your blowpin, you'll see that the main pressure drops very quickly. But probably the last, let's say 70-80% of the air pressure, which is only a very small amount, so the last 20 psi, takes the most time to get out. Now that's another reason why we've got to have a larger diameter blowpin tube. If the air can't get out quick enough, it's going to extend your exhaust time. So we've got to make sure that we can get the air in fast to inflate the bottle properly at a reasonable rate, but we've also got to make sure that we can get the air back out as quickly as possible. Now again, coming up to 100 psi on air pressure is absolutely critical. If you don't have that pressure, then you're not going to get that heat exchanging process going on. Therefore, you're going to get hot and cold spots in your bottle. You're going to see quality issues with dipping panels as well. So, we hear a lot about recirculating air and chilled air. So I'm just going to quickly touch on that right now. So recirculating air is absolutely critical to all blow molding processes. Now, why is it so important? Well, one of the things I learned was when I was a toolmaker, was when I was heating up steel, as you can see in this photo, and then we used to dunk it into a bucket of oil. Now, the idea of that oil was to create a change in the molecular structure of the steel. So what my boss used to tell me about was very simple. When you dunk the hot steel in the oil, if you don't swirl the steel in the oil, then the oil around the steel will heat up very quickly and then reduce that heat exchanging process. So it's no different to when we inflate a plastic bottle. We have to turn the air over or circulate the air inside the bottle to make sure that we're getting that heat exchanging process happening properly. But equally important, we've still got to maintain that pressure. So if we're running 100 psi blow air pressure, I would actually bring my blowpin down and I would have roughly a 10% delay for the blowing sequence at full pressure before I bring on the circulating air. So the full pressure brings the parison out into the shape of the bottle, and then we turn on the recirculating air. Now the recirculating air exchanges that heat from the inside of the bottle, but the pressure still needs to be remaining quite high. So I would only drop the pressure by 10-15 psi on my recirculating air. Now if you have a gauge mounted to your blowpin, you can see that and you can gauge it. So we've got to make sure we maintain that pressure inside the bottle. So chilled air. Chilled air is another component that you see here. I've borrowed this one here from a chilled air supplier. So what they do is they actually circulate the air. They circulate it with very, very cold air, minus 40 degrees temperature in many cases. But what they try and do is they try and target the hot spots in around the neck, around the handle, and the base of the bottle. So what they do is they use the air turbulence. They use very, very cold air to cool the bottle from the inside. Again, you've still got to maintain that wall pressure. So, a couple of quick things to work on. Work with facts. Question anything you're not sure of. Pressure is the result of resistance to flow. Now, that was a big component of what we talked about today. So know what your inputs are to get a predictable result. Know and measure your variables, and never ever trust a computer. You never know what they're trying to tell you. So compressed air, really, really important in your process and the final step of the heat exchanging process. Go away, do some homework, find out what your air pressure is, and if it's not correct, if it's not at 100 psi or greater, do something about it. Do it very, very quickly. And also make sure that your blowpin diameters are as big as you can possibly have them. Okay, that's it for Module 3. I hope you enjoyed it. More importantly, I hope you go and use this information. All the best, have a great day. Until then, have fun blowing a bottle.